Started. Honor those people who are here on time. Okay. So today we're going to do a bit of review from CHEM. Remember the propagation of uncertainty that you were required to do? Do you want a review of that? Or should we just skip this and get ahead? Review? Okay, let's do that. And then there's another thing too that we will review. It may not be review, and that is really just focusing in on how to propagate uncertainty when it comes to like a calibration curve. So like we'll see how we apply it to experimental results and specifically calibration curves or linear fits. Okay. And so why do we want to propagate uncertainty? Well, a number without a estimation of its uncertainty is useless. So if I tell you the answer is 15 and I don't reveal that I'm uncertain in the first digit, like 15 plus or minus 10, then I've misled you. I mean, you might assume if I don't give the uncertainty that it's plus or minus 1. And that would be a dramatic assumption, if my real uncertainty was plus or minus 10. So you really need to communicate both your answer and then your sure. How sure are you? Your estimate of your uncertainty. So directly measured quantities, if you make one measurement, typically you can look at the instrument or the piece of equipment like a balance. If you measure a 4-place balance, you look on the box when you buy it, it'll say that, the uncertainty is plus or minus 0.0002. But that's for a single measurement. Once you make two measurements, what's the uncertainty? Because every measurement on a balance is really two measurements. How is that so? Why is it that I'm taking two measurements when I just put something on a balance and measure its mass? Yeah, exactly. So there's uncertainty in the zeroing part. So everything we do really is a difference. And so this is for a single measurement. So it's 0.0002 for the tearing. There's plus or minus in that, and then for the actual number that you measure. Okay. Multiple measurements also incorporate other uncertainties. And so that's your first measurement, and then you have a volume, or if you have other masses and so on, then the uncertainties just start piling on top of each other. So that's why we want to propagate uncertainty, to see what our sources of uncertainty are and to attack them if we want to increase our precision. So there's really a couple of reasons. You want to know what your uncertainty is, and then if it's too high, this practice will give you a guide in how to reduce that uncertainty. So we'll look at that as we go through. We'll say, oh, here's where my uncertainty is largest. So that's the measurement I want to focus on if I want to reduce my uncertainty. And so we'll be using the skills that we learned last time about the mean and the standard deviation. And so we're really going to be focusing today on this standard deviation. So here's our propagation of uncertainty equations that we have in CHEM. We have different operations like sums and products, exponents, logs, and anti-logs. And these equations here really just come from taking the derivative. You can derive all of these by taking the derivative of y with respect to A, and with respect to B, and with respect to C. And that's where those dy by dA would be this uncertainty A, and so on. So you could do this, you could derive all of these. So all of these are essentially the results of taking the derivative of these various equations. We can simplify these things in a couple of cases. Like if you have the uncertainty divided by the value itself, that's the relative standard deviation. So it's the standard deviation relative to the value. And so in this case, if we have this mathematical operation of A times B over C, then this is the RSD for A, the RSD for B, and the RSD for C. So notice that it's just the sums of the squares of the relative standard deviations. Now, if I move y over onto this side, then that's the relative standard deviation of y. And if I square it, I get rid of the square root. And so this is a simplified equation here, that the relative standard deviation in the result is just the sum of the squares of the relative standard deviation of each individual piece for multiplication and division. For addition and subtraction, the square of the uncertainty in the result is just the sum of the squares of the uncertainties of each individual piece that you're working with. So these are easy to remember. If it's addition and subtraction, you're just looking at the variances, the squares of the standard deviations. If you're dealing with multiplication and division, you're looking at the sums of squares of the RSDs. And so that's an easy way to remember it. If you're doing in exponents, essentially that's a times a times a. So take that RSD for a and multiply it by x times, and that gives you the RSD for the result. Logs and anti-logs, for base 10, they have this conversion from base 10 to base E, etc. in here. So let's do an example. This is an example from CHEM, so this will be a bit of review as well. But we'll talk about uncertainty analysis in this one. So we have this metallic object, weighs 2.5 grams, and it displaced this much water, 0.13 mils of water. And so what's the density? And can you tell if it's gold or tungsten? So gold has a density of 19.28, tungsten 19.25. So pretty similar densities. We could take this mass and divide it by the volume and calculate our density. So we look at this and we see that it's 19.25. And if you were a freshman, you would say, done, right? It's tungsten, 19.25. Okay. But look at the problem. We have some uncertainties associated with it. So as a freshman, you wouldn't know what to do with those. So let's see how these uncertainties figure in to this calculation. Now, which kind of uncertainties are we going to use? This is our calculation. So how would we find the uncertainty in the density? RSDs. Yeah, we would use the RSDs. So what are the RSDs? Well, it's the standard deviation divided by the value. So the RSD would be this 0.225 divided by 2.5. So that'd be the RSD for one of them. The other one would be the 0.05 divided by the 0.13. That'd be the other RSD. You square both of those, add them together, take the square root, and that's the RSD in the result. Okay. We're going to keep all of these digits as guard digits, so that's another vocabulary word. When you keep all of these digits in the intermediate calculation, we're going to just hold rounding to the end, and so those extra digits are called guard digits. You really don't need to keep 4 or 5 of them. Just 1 or 2 extra is fine. I always keep 2 extra. But, I mean, if you're working in your calculator, just let it go. Let it keep all of those. If you're going to write them down, maybe to use again later, go ahead and write down quite a few of those digits just so you don't get into rounding errors. You don't want rounding to impact your uncertainty analysis. Okay. So here's our calculation. So here's the original result, and now we have that multiplication equation. So this was the uncertainty, and the result was the value that we calculated, this 19.25. So in the original sort of table of uncertainties, that was y. So in this case, rho was y in that table. So here was y times the square root of the 2 RSDs squared and added together. So RSD number 1 would be this 0.225 divided by 2.505. So that would be the first RSD, and this is the second RSD. Now, which of these uncertainties is the largest? It's tempting to say the 0.2 is the largest, but we're dealing with relative uncertainties when we're dealing with multiplication and division. And so this is where you do your uncertainty analysis. You're comparing RSDs. So look at this RSD. Let me just say it a certain way. This is 2 parts in 25. Do you see what I did there? 2 parts in 25. I moved the decimal place over to where I just had 1 digit of uncertainty, 2. And then I looked in the denominator. What's the denominator? So 2 parts out of 25, or 2/25 is this RSD, whereas this is 5/13. Did that leave you behind? I see a bunch of nods. This is 5/13, and that's 2/25. Which is the largest? 5/13 is much larger than 2/25. Okay. A 2/25 is 1/12. Okay. 5/13 is almost like 1/3. It's a little bit more than 1/3. So 1/3 versus 1/12. So this is the problem for our uncertainty, is our volume measurement. So immediately I know just by comparing the RSDs, and I could have done that in the original problem. I could say, wow, this right here, 0.05 uncertainty and 0.13 mils of displacement, that right there is telling me I have a RSD of about a third, a little more than a third, and that's a big problem. So I don't even really need to know like all of the detail. I know that my uncertainty is going to be about a third, and that's going to be a problem. Okay, so we'll see that later. But I just wanted to say, when you get to this step and you can see the RSDs right next to each other, you can easily pick out the one that's the problem. Okay. So if I wanted to improve my analysis, and I can't really change the burette, like this is the burette uncertainty, right? The little tick marks that I have that are at 0.1 mil, and I can estimate to half a mil. So this is the glassware that I have. How can I improve my uncertainty in this case for this experiment? I'm really stuck with a burette, and the volume measurement is my problem. Even though my mass, it looks like I could really improve my uncertainty in mass, it's the burette that's causing me the problem. So let's focus on the burette. How can I improve my uncertainty if I can't change the glassware? That would change, it wouldn't change this uncertainty. So more measurements, I don't know that I could get any more precise than what the burette's going to give me. So I'm really stuck with the 0.05. So how could I change the 0.13? There's two pieces to this relative uncertainty, this relative standard deviation. How could I change the 0.13? Yeah, which means I need what? A bigger sample. Right, I need a bigger sample. I need a larger piece of metal, whatever this metal is. Right now, it only displaces 0.13 mils. And so if I had a bunch of those or more of those, then it would displace more water. So I would still have an uncertainty of 0.05, but if it replaced half a mil, then that would be 1/10 a relative standard deviation instead of 1/3. And so, then I'm getting better, right? So if I could get 3 or 4 pieces of metal and put them in and make sure there weren't any bubbles or anything like that, then I get a bigger displacement. So I've increased the denominator. I couldn't decrease the numerator, but I could increase the denominator. I could measure a bigger sample, and that would reduce my uncertainty. And that would make this measurement more precise and help me determine whether it's tungsten or gold. Okay, so then we calculate this. You take the fractions, you square them, you add them, you take the square root, you multiply by the result, and you get 7.6 grams per mil. So this is my reported value if I want to keep 2 digits of uncertainty here. It's 19.3 because this is what tells me where to round. And it's the convention is either to keep 1 or 2 digits of uncertainty. I know we said in the significant figure convention we keep 1 digit of uncertainty, but I see a lot of times people report 2. And so here's our uncertainty, 7.6 and several other digits, but I'm just stopping at the second digit of uncertainty. So that tells me that I round at the 10th place. So this is my 7.6, so I have to round this result at 19.3. So I went up there and I rounded at the 10th place so that they match. And that's the one thing I want to point out. These two place values must match. So they must have if they go to tenths, they both have to go to tenths. If they go to thousandths, they both have to go to thousandths. And we want to keep a maximum of 2 digits of uncertainty. So those are best practices. And so now we have a problem. It's 19 plus or minus 8, or 19.3 plus or minus 7.6. And so we can't tell the difference between gold and tungsten at all. Okay. And so if we wanted to sort of plot these uncertainties, here's the volume. It was 0.38. I said it was a little bit more than a third, and it was. So 0.38 is the RSD for the volume. Big wide distribution there. A narrower distribution for the mass. This is 0.09 is the RSD for the mass. Squaring these values and adding them together and taking the square root, we get the overall result. So the 0.38 squared, 0.09 squared, take the square root, That's the RSD for our result of 0.39. Notice how it's very close to this one, 0.38. The mass uncertainty only added one more, step to that, 0.39. So we could look at these values and say, which one of these is the one that's given us problems? It's the 0.38, it's the volume. So if we can measure, much more of this metal, we might be able to be more precise in our answer. We might be able to tell the difference between the two. If we got a really large piece, we could get a very accurate volume or, in precise measurements. This is all of these metals. So I don't know if it's every metal on the periodic table, but it's a lot. I typed in their densities and I plotted them, and I made the intensity of this. I put it onto a Gaussian curve that had the same mean as our result and the same standard deviation as our result. So this is kind of the bell curve of our experiment. And this is showing all the metals that fall under that bell curve. So some metals have a higher density than what we got, like iridium, and a lot of metals have a lower density than what we got. Okay. And then this green envelope here captures half of this curve. It doesn't look like it, but it captures half of this curve. So this piece on this side and that piece on this side added together match the area of this area inside the green area. And so if I wanted to say that here's my mean, here's my standard deviation, I know that the thing I measured with my equipment is somewhere close to that mean. It might be higher, it might be lower, and to capture half of the distribution, these would be the metals that would fall within the 50% region of this distribution. So I'm 50% confident it's one of these. And sure enough, gold and tungsten are in there, but it could also be tantalum or iridium or osmium or platinum or rhenium. So, and it's a 50-50 shot. It could also not be those. So I could flip a coin and it's one of those or not one of those. Okay. What about 95% confidence? So if I take that standard deviation and I multiply it by 1.96 in both directions, so 1.96 times my standard deviation gets me all the way up here almost to 35 grams per mil. And then, multiplying it by 1.96 and subtracting it from the mean gets me over here just below 5. So I'm 95% confident that the metal I tested is somewhere between these purple values, and these are all the metals that would capture. So I'm 95% sure it's one of these. Okay. So it's a pretty crummy experiment, but it's not useless. Okay? Because look on here. Magnesium is not on here. Magnesium is down here. It's one of these really non-dense metals. I don't know what the word for non-dense is, right? It's not light. Light is mass. What is density, right? It's dense or non-dense. I don't know. Is there an opposite word for dense? Sparse? I don't know. Like for population, we would say sparsely populated, but we would say magnesium is a sparse metal. That doesn't really make sense. But I've always, whenever I get to this point, think, what is the word for non-dense? It's just non-dense. And so I'm 95% sure it's not magnesium. So that's worth something, right? And in forensics, we're dealing with comparisons. And so I don't need, from a forensic standpoint, if someone said, test to see if this is magnesium, we only have a tiny little piece. It's 0.13 mils. You put that in your little, graduated cylinder or burette, and you calculate the displacement, and you say, okay, it's, whatever, 0.13 mils, plus or minus 0.05, and then you measure the mass, and it's whatever it was, and you say, okay, the density is 19.25. I do my uncertainty. Okay, well, it's 19.3 plus or minus 7.6. It's not magnesium. How sure are you? Well, I'm at least 95% sure it's not magnesium. I could calculate the distance of magnesium to my mean and compare that to my standard deviation and tell you exactly how sure I am. There'd be like a 90, for me to get that result, it would be like a 1.5% chance, okay, that would be magnesium giving me this number, okay, which is way below 5% or 2%, 2.5% on either side. So it's, from a forensic standpoint, this may work. It's not beautiful, doesn't have a lot of precision. It's 7.6 grams per mil uncertainty. But again, if in comparison, if you're doing a forensic analysis and you're being asked to compare, is this magnesium, you could say, even with this crummy precision, that, yeah, it's not magnesium. So that's pretty cool. You say, yeah, but the math worked out so that the number was so close to tungsten. And that's just an accident, okay? You really don't know because of your uncertainty. Okay? So I say there are no yeah buts. It's like, I wanted a hat when I was little, when my kids were young, because I would say, did you do this? And they, yeah, but, and I was like, my name's not yeah, but. So anyway, that was their phrase, yeah, but. And so every measurement has uncertainty, and bridges in Minnesota have fallen because of this, or we've skipped vehicles off of Mars by miscalculating uncertainties. And so we can't tell with more than 50% confidence that it's one of those. So let's look at this linear calibration example. So we have this external calibration curve. And you've seen curves like this. Okay, this is our standard. We put in, say, several aliquots of parts per billion cocaine and analyze those, say, in a gas chromatograph or liquid chromatograph, and we get these area counts. And we see it's definitely a very sensitive technique, because look at the slope. This is, the slope is 416. So if I change the parts per billion of cocaine by 1 part per billion, my Y signal goes up by 416. So that slope is what we call sensitivity. If you change it by 1 part per billion, you get a change in signal by 400. Sometimes it's even better than that. It's in the thousands. So that's fantastic. So we've got a pretty good sensitive technique. Where it hits the y-axis would be where the parts per billion cocaine goes to 0. We still have sort of a blank signal of 1,214. Okay. So this is our calibration curve, and if we make some unknown measurements, we put that in, we get 3 values of area counts. And we could calculate the standard deviation for that, but that tells us our uncertainty in the signal. It doesn't tell us the uncertainty in the concentration. And so this is the most useful role of propagation of uncertainty, is turning your Y values into X values and their uncertainties. So have you ever come across this? Did y'all have to do this in quant or instrumental? Right? You did calibration curves, but did you ever calculate your uncertainty in your result? You may have done the conversion 3 times and then calculated the mean and standard deviation of your result. Yeah, and that's good, okay. But from this, like, we can do this and we can do it that way, but let's propagate the uncertainty. Let's take our uncertainty in Y and see how we can calculate the uncertainty in X. Okay. And so we have these 3 X values. You could take the average of those in the standard deviation, and it would give you the same answer. Okay. So this trend line is not useful because it doesn't have uncertainty estimates. And so if I'm ever on any of your little research committees or things like that, or you give a talk and you show a trend line like this, okay, I'm going to ask you, what's your uncertainty in the slope? What's your uncertainty in the intercept? Because you see, this trend line gives us our slope and our intercept, but it doesn't tell us how certain we are. It gives us this R squared value. Do you know what the R squared value tells you?
All the points are on the trend line?
Yes. So there's some scatter in the points, right? So these points are scattered. I'll call it scatter. And this is a percentage of the scatter. Weird to write over my shoulder. And so what is the model? So this is the typical language, the percent of the scatter captured by the model. The model is y equals mx plus b. So that trend line is the model. You're modeling the data with a line. And what percentage of the scatter does that capture? 99.94%. So that's really good. And so this is a very good calibration curve. And so if we do the full ANOVA, so we put in the X values as our X values, and we go to data analysis and put in the Y values as your Y input, and there's a checkbox for making the intercept 0 or not. We leave it unchecked because we don't want to make the intercept 0. We see that the intercept is 1200, so we let the model the intercept, and then we get the ANOVA. We see that the R-squareds match and everything's good. And down here at the bottom, we have our coefficients and our standard errors. And you did this a bunch of times in PChem. We did this linear regression analysis. And so these are our values. This is B and this is M, and these are the uncertainties in B and M. So this is what our calibration curve should be. So if you're going to put out a model like this, go ahead and do the ANOVA and tell us what the standard deviations are for those values. So do you see where these numbers came from? This one here, this 120 came from down here, right there. And then the 5.9 came from this right there. And then what's our confidence in those? 1 minus the p-value is our confidence. Okay, so we'll talk about this confidence more later when we get into p-values and null hypotheses and so on. But 1 minus p, so this is 0.4, so I'm about 1 minus that. Let's see, yeah. So it's close to 0.5. So I'm about 50% confident that standard error is real, if you want to think about it. Or it could be real, or it could be caused by random fluctuations in the data. So that's about a 50-50 chance that it's caused just by random fluctuations in the data versus it being an actual dependable number. And then this one is 10 to the minus 6. So there's like a one part in a million chance that random noise in the data gave you that slope. Does that make sense? Look how clean that slope is. This is saying there's a 1 in a million chance that the random noise in the data gave me the data points all lined up in a line, and I got that slope of 416, which makes sense, right? We're very confident in the slope, not so confident in the intercept. For this class, we'll go ahead and use that intercept, but in a couple more lectures, we will not. We would throw it out and redo the ANOVA. Okay. So if we're given a y value and an sy, how do we find sx? So this is the exercise that we're doing. This is the thing I really want you to know. So if you are starting to fade, stretch, wake yourself up. This is the meat of today's lecture, is this piece right here. Okay. So here's all of our values. Here's our calibration equation. M is 416.6. Sm, the uncertainty in M, is 5.9. Go ahead and keep your units so that we can see how the units all work out. It's area counts per parts per billion. That's the slope units. The intercept is in area counts. It's the y-axis. And here's the uncertainty, B and SB. So does everybody comfortable with the terminology? M and SM. SM is the uncertainty in M. Okay. And then we ran 3 check samples. So here's our 3 Y values, 57,000, 55,000, and 54,000. So those are our 3 Y measurements. We can average those at 55.333, and the standard deviation is 1527. So this would be Y and SY. So these would be our uncertainty values. So Y and SY are given here from this table. So with this information, we should be able to calculate X, and we should be able to calculate SX. So X is easy. We have Y equals mx plus b. Let's subtract b from both sides and divide by m. So X is equal to Y minus b over m. Simple algebra. So we calculate it 55, 3 through 3, minus the intercept divided by the slope. So it's 129.9 parts per billion. So that's pretty easy. Like I said, in instrumental, you probably would have calculated X for this one, X for that one, X for that one, take the standard deviation, etc. And that would work as well. But it'd be nice to know what our uncertainty is from our particular analysis. And so what is our SX? So let's calculate this. All right, so when we're calculating the uncertainty and we look at this equation and we compare that to our uncertainty equations, so look in your notes, find the little table that has, addition and subtraction, multiplication. What do you see with this equation? Which one of those do we use? Yeah, it's a combo. So that can be a problem, right? We've got subtraction in the numerator and we've got division as well. So we've got to do this in two parts. Now, you did this in two parts when you calculated X. Which piece did you do first? Did you do the subtraction first? Yeah, we did the uncertainty that way too. So if you did the subtraction first, let's do the uncertainty for that numerator piece first, and then do the division second. So let's keep our order of operations the same as we would in doing the actual calculation. So the numerator is Y minus B, and this is all color-coded for you. We have the numerator, Y minus B. We could calculate that, and that's 54,119 counts. That's our numerator. Let's calculate the uncertainty in this number. So we can calculate the uncertainty for the numerator. So I've got this new term, numerator. I didn't give it a variable. I'm just giving it a name. And so we could calculate the uncertainty in the numerator. So everybody clued into what we're doing. We're doing the numerator, and we're going to get the uncertainty in the numerator so we can use it in the division piece. Okay. So here's the uncertainty in the numerator, right? It's the variance in Y plus the variance in B. So we've got the 1527. That's from over here on Y. That was this one down here. And the uncertainty in B was up here. And so we have those two pieces here. Square them, take the square root, and here's our uncertainty in the numerator. Now let's do the division piece. So again, color-coded. Now we're working on the green part of the problem. Okay. We can do that division, we get the X value, right? We have the 129.9 times the square root of the RSD squared. And I guess this is the piece that people mess up, okay, the most. One, they forget to do the numerator and the uncertainty in the numerator. So the numerator here goes down here. And the S numerator goes here. What I see most common is people will put in the M and SM here, like the slope and the uncertainty for this. I mean, they'll put B and SB here, which is just a part of the numerator uncertainty. They didn't get the Y piece, and so that's where they messed that up. And so we come over here, we get the numerator and the uncertainty in the numerator. And so this is now the 1532 divided by the numerator value of 54,000. Put all those pieces in your calculator, and we end up with 4.1 parts per billion. So that's not too bad. I mean, it's 129 plus or minus 4, or 130 plus or minus 4. So this is another way you could write your uncertainty. You could do 129.9 and put the plus or minus uncertainty in parentheses, or you could just put the numbers in parentheses. So this is another way to write it. You could say x equals 129.9, 4.1 ppb. So when you're putting this into parentheses, you're implying, since you have two digits, that those digits are uncertain in this right here. You could also write it, if you wanted to just keep one digit of uncertainty, you could write it 130 and put a 4 here. That's probably the most compact way. And that 4 being in parentheses and only being one digit is saying, okay, that's my uncertainty in the adjacent digit. So when I include 2 of these, I'm replacing the plus or minus goes in the previous 2 digits. When I'm just writing one digit, the uncertainty is just, active in that next digit. So we're just sort of using the place value in the parentheses to show us where our uncertainty is. If I'm going to do this in all cases, I really need to say, if I'm writing the paragraph and I'm talking about this, that these are standard deviations. So I would write a standard deviation if they were 95% confidence intervals, then I would say that. So those are your two choices, your confidence interval in parentheses or plus or minus, or just your standard deviation in parentheses or plus minus. But you've got to communicate that, because if I just see this, even though I know the uncertainty, I'm unsure as to how wide you've put your bars. If I'm just pointing out that it's plus or minus 1 standard deviation, that's a 64% confidence interval. Okay. If I wanted to report a 95% confidence interval, then I would take this 4.1 and multiply it by 1.96. So let's go ahead and do that. Someone on your calculator, calculate 4.1 times 1.96.
8.06.
8.06. So 8.1. So our 95% confidence interval for 129. So it's gone up, it doubles. 1.96 is very close to 2. Okay, but it's exact. If you want an exactly 95% confidence interval, then you multiply by 1.96, and that gives you your 95% range. So I'm 95% sure that my value for my 3 check samples is 129.9, and it's within 8, plus or minus 8. So where does this error come from, or this uncertainty come from? Can I get you that close? It comes from little fluctuations. Where are these fluctuations? Well, they're in your techniques to some degree, your pipetting techniques, your weighing techniques, but also in the flow rates of a GC. The gas is flowing through all of these little columns and so on, and there's pulses, there's temperature in the oven, the temperature control of the oven can fluctuate, your detector can fluctuate, and every one of those can move your signal high or low. And so if we have just one fluctuation, it can bump it high or low. If we just multiply this out to infinity, we get this Gaussian distribution. So this little bump high and low, if you have sort of measurable fluctuations, it's Pascal's triangle. And does anybody recognize this Pascal's triangle from one of your previous courses? What course did you see that in?
PChem.
Where'd you see it in PChem?
I was going to say
Quant?
Or
Calculus. I would have expected you to have seen it in organic, maybe organic too.
peaks.
Yeah, which peaks?
The
The splittings.
Triplets and- yeah.
Yes, triplets, doublets, quartets. What was that from?
Like the HNMR.
Yeah,
All
the
of
proton NMR. Yeah. So adjacent protons are behaving like fluctuations, and they're spin up, spin down. You get these individual intensities. And so you've seen the individual fluctuations of neighboring protons causing your signal to jump high or low. The neighboring could be high and yours is high and it bumps one way, or it's low and yours is low and bumps the other way, or they cancel each other out. And so you have this middle one, two fluctuations. And so this is the intensity pattern of the spin-spin coupling in NMR for like proton NMR and so on. But if you have like a infinite number of adjacent protons, it's just going to smear all of that out and you're going to get one big broad peak, a normally distributed broad peak. We rarely measure those individual fluctuations. It's in terms of our instrumentation. So we end up getting Gaussian peaks, really smooth peaks of varying widths. Okay, but it's nice to see, sort of connect that to NMR, where you can actually see the individual fluctuations of neighboring protons causing your signal to hop high and low. Okay. If you take that Gaussian distribution and you assume, this is a big assumption, that your data is being smeared randomly by these minuscule fluctuations, and you have an immeasurable quantity of them, then we would assume that it's a Gaussian distribution. So whenever we take the mean and then we calculate the standard deviation, we consider it a Gaussian distribution, and that's where we justify this multiplying of 1.96 times that uncertainty gives us a 95% confidence interval. So that 95% confidence interval is a Gaussian assumption. Okay. If we look at the data, if we were able to get the population, we might see that it's bimodal, or that it's skewed high or skewed low, and we'll look into those statistical tests next time. Okay. And maybe in 2 lectures. But assuming things are Gaussian, then we can take this idea of confidence intervals and report our data that way. Yeah.
You get the 1.96 because we're assuming it's Gaussian. Is that something?
Yes. So these are related. So these values of how many multiples of your standard deviation give you the area under that curve. It's the area under a Gaussian curve. And so that's what's being shown here. These are 3 results. This top one is plus or minus 1 standard deviation. I said it was 64%, but I was wrong. It was 68.3%. So this is plus or minus 1 standard deviation. So when we said it was 129 plus or minus 4.1, that is this one here. It's 68.3% confidence. That's our 68.3% confidence interval when we use plus or minus 1 standard deviation. It's not nothing, right? We're confident that 68% of there's a 68.3% chance that the true mean is within that interval. Okay. We don't know what the true value is of that cocaine sample, but we got 3 Y measurements. We calculated the X measurements, and we're 68% confident the true value is within plus or minus 4. If we did the 1.96 for that, it was 129.9 plus or minus 8.1, and that was our 95% confidence interval. Okay, so that 8.1 is capturing 2 sigma plus or minus, well, it was exactly 2 sigma, exactly 95% confidence. If I did 2 sigma instead of 1.96, I'd be at 95.4% confident. And so that's why we use 1.96. Plus or minus 2 times that standard deviation would be 95.4% confidence interval. And so just to keep it clean, at 95% confidence, we just multiply by 1.96. If we did plus or minus 3 sigma, so we're looking at 4 is our uncertainty. So now we're dealing with 12. So 129 plus or minus 12 would be 99.7% confident. So the more confident you are, the wider your envelope, right? It makes sense if I'm gonna say the heading is like 90 degrees plus or minus a few degrees, in terms of where something is. Or if I want to be 100% sure, and I know it's to my right, it's 90 degrees plus or minus 90, right? It's somewhere that way. I don't know if it's that way, but the wider your range, the more confident you are. So this idea of this confidence interval, I've been using it this whole time. It's that range of values that is likely to contain the true value. So at 95% confident, that means your true value is outside of your range 1 time in 20, right? So that's still not very good, is it? 1 time in 20 analyses, it's going to be outside of your range at 95% confidence. Okay, so that could be a problem. So this is assuming the standard deviation. Assuming the Gaussian. So this is even 99% confidence stinks, even though it's like almost 3 standard deviations. But these are some of the ramifications we have from 99% confidence. That's a lot of mail lost every hour, or unsafe drinking water 15 minutes per day. Which 15 minutes? Who knows, right? It's random. Or 5,000 incorrect surgeries per week, or 2 long or short landings at most airports per day, or 200,000 incorrectly filed prescriptions. That's scary. So, if 1% of the prescriptions were wrong, it would be 200,000. So, and no electricity for almost 7 hours per month, or with 16,204 murders. This was a 2008 figure. That would be 162 wrongful convictions. So dang, I thought 95% confidence was good. So how do we address this? We don't want 162 wrongful convictions. So what is our option? To go to 99.999% confidence? Then the results are so uncertain, you're almost not meaningful. So put yourself in the crime lab. You're analyzing evidence. How do we get around this problem? What?
Do the test multiple times?
Multiple times is one way that could decrease your uncertainty. Okay. Do we have to use GCMS? Let's say this experiment was GCMS. It's probably the gold standard, so it's really good. You're on track with something, though. You're thinking of substituting this method with something more reliable, right? But what if we don't substitute? Can we add? So let's keep GCMS, and let's operate that at 95% confidence, even though that's scary. Can we add techniques? Like if we have a GCMS analysis that's 95% confident, and some things might slip by that, what if we added a technique that was also being operated at 95% confident? So are there any other things that can detect cocaine? Yeah, IR. Is IR the same as GCMS? Would it measure exactly the same phenomenon? What is GCMS? It's boiling point, it's a mass spec or whatever. In fact, if we were doing GCMS, we'd have the retention time, which we could say has a 95% confidence interval in terms of its retention time. Then we have the mass spectrum, the molecular ion. That's totally different than the retention time. We could have 95% confidence on that. And then we have an IR. Maybe there's a peak associated with cocaine that is going to have a plus or minus. We could be 95% confident on that. So we could add techniques, all three operating at 95% confidence. Now, what are the chances that what they call the Swiss cheese effect, right? You look at Swiss cheese, you can't see through it, but maybe there's an angle at which you go through all the holes and the holes line up, right? What are the chances of that? Well, we can calculate that. If each of those techniques is operating at 95% confidence, so we have this technique, it's 95% confident. Let's call it a two-tailed technique. And so over here and over here, we have a 2.5% chance. So 0.025. That's the percent chance that the true value lies over here somewhere. Okay. And then we couple that with another technique, and it's completely different. But we got unlucky, right? It's now over here, and it slips through that 2.5%. So this was retention time. This was molecular ion or mass spec. And then we did the IR. And for whatever reason, this didn't look like cocaine. Okay. And it slips through, say, some other, 2.5%. You see how unlikely that would be? That's 0.025. So for it to slip through the wings of three different techniques, and each wing is 2.5% chance of it slipping through, what's the overall probability? It's the multiplication of those. So someone get your calculator and multiply 0.025 times 0.025 times 0.025.
1.56 to negative 5.
1.9656, okay. To the negative fifth. So let me just get rid of that decimal place and put the zeros on there. Okay. So that was 5, 1, 3, 2, 1. So now we're dealing with 1 minus that would be our confidence. So 99.998. So if we add techniques that are unrelated to each other, we can really, really increase our confidence. And we can't really operate a GC at 99.998 confidence. Our intervals would be so wide that it would almost be useless. But we can operate our GC with reasonable 95% limits, our mass spec with 95% limits, and our IR. And so that's why they require multiple techniques to make a judgment, to make a ruling, right? Do you want an IR plus a GC plus an MS? That'd be great if you had 3 of those types of techniques. So that's why we layer these on top of each other so that something doesn't slip through the wings of one of our analyses and we have a wrongful conviction.
Okay. Imagine how unlucky you are.
Yeah, you'd have to be that unlucky. Right? And so it's not impossible, though. That's a scary thing. So that's what, in the same thing that we're talking about forensics applications, but this is the same thing with quality on your automobiles, the strength of the cords on your parachute. I mean, everything that is mission critical has got this kind of analysis. And so this is where the Six Sigma comes in. Six Sigma is a quality organization and mindset that attempts to design quality into the process. And I'm not so sure yet, but if it's not Six Sigma, it's something similar in the crime lab. Okay, that you're trying to design quality into the process so that the analyses that you do are above reproach. And so this is the Six Sigma goal of having less than 4.3 defects per million opportunities. Now that's the key piece right there. One piece of evidence is not a single opportunity. Think of all the things you do with that evidence. You dissolve it, you dilute it, you put it on the instrument, you analyze the data. There's lots of opportunities for a mistake or a defect. along that process. Just like an automobile. Think about how many parts are on an automobile. They want to have less than 4.3 defects per opportunity. They're tightening the lug nuts. Those are 5 or 6 opportunities for a defect. And there's more than a million parts on a car. So every car, even operating at the best quality level possible, is going to have, if there's a million opportunities, roughly 4.3 defects. It's just impossible to build something that complex without any mistakes or quality errors or quality issues. But what you want is you want your mean and standard deviations to be 6 sigmas away from your specification limits. And so like if this is the specification limit for saying it's not a crime, right? And this is the evidence level, you want your certainty about what the evidence value is to be so narrow that there's less than 4.3 chances out of a million that you would get a wrongful result. And that's a gold standard, and think about that. If this is the limit that you're worried about, you definitely want your data to be that tight so that you can be far away from your limits. And as your value gets lower and lower, you're going to start reaching this region right here. And so your confidence is going to start to decrease. And so then you would set a standard. If we're below here, then we can't say. We would say it's indeterminate. You can give a number here, but you're not confident. So you would just say that's indeterminate. It's not high enough for us to be confident that it's in the range of relevance. Okay. There's some supplemental information. It's just more examples and practice problems and so on. So let's go through a few of those. We've got a little bit of time. Notice that in all of these examples, jumping from the result to the uncertainty to the relative standard deviation should just be second nature to you. So if I have this problem up here, a 1 mil standard containing this many milligrams per mil was used to prepare a stock solution, and then a syringe was used to transfer this to a 250 mil volumetric flask, and we'll calculate what is the final concentration. So notice that we've got a number written like this. And so how do we convert that into, say, a standard deviation and a relative standard deviation? So we're looking up here. If I've got a number written like this and it's milligrams per mil, okay, the uncertainty is this. Can you see that? Right, this right here came from, this is so hard to do. Okay, that number right there. You see the parentheses, and do you see the previous place value? Previous place value is in the hundredths place. And so the uncertainty is plus or minus 1 in the hundredths place value. So that's this right here. 0.01 milligrams per mil. My relative standard deviation is really easy to calculate, but I still have to know where the place value is for my uncertainty. It's 0.01 divided by 1, so that's my RSD. I haven't talked about coefficient of variation, but it's the RSD times 100%. Okay. It's typically in percent, yes.
So when I'm looking at that one, I guess I'm confused as to why it needs a hundredths place. Wouldn't it be 0.01 plus or minus 0.01?
Mm-hmm. It is. That's the tenths, hundredths.
So that's the place right next to the one that it's next to.
Yeah.
Okay.
Yeah.
Okay.
So it's just the previous place value.
Okay.
So it looks like it's in the thousandths, right? Because it's 3 away from the decimal place, but it's replacing the number that it's next to.
How I was looking at it, it looks like a ones place.
Yeah.
It's plus or minus 1. You know what I mean?
Oh, right, right. No, we're just giving you the digit and putting it next to the value that it replaces.
That makes sense.
I'm so glad. I cover this a bunch, and it's the thing. I think a lot of times people think they get it, but they're wrong in how they're getting it, right? So that's why I wanted to do these extra results. So and then this one is written with percent, so that's kind of a mess. Right? So what do you do with that?
Fine.
That's a coefficient of variation. That's a CV. So this guy right here, where's my pen? This right here is a CV. So we're right here, we know the CV is 0.03%. And so then we divide that by 100% and we get, this is the RSD right here. So this is just a mess, but this is what you see in the literature all the time. You see people report uncertainty in percent. You have to assume that's a coefficient of variation. So then you got to get to the RSD, which then means you got to get to the actual uncertainty number. And so we know that 0.003 is equal to the uncertainty divided by 250 mils. That's this guy right here. Okay, and so then rearranging this, this number is right here. And so we rearrange this, 0.0003 times 250 mils gives us our uncertainty. Okay. And so this, you need to be good at this, going back and forth, and percent error, and RSD, coefficient of variation, the mean values, and so on. Because this is every day you do stuff like this, trying to figure out how to manage uncertainties. The same kind of thing here. We've got this 250 microliters plus or minus 0.5%, so that's a CV as well, right here. So that's 100 times equals 100% times RSD. So we would rearrange that. So here's our RSD, which is equal to our uncertainty divided by 250. And so we could solve for that. It's 0.005 times 250 microliters and 1.25. I can't unsee this now. When I see that mu, I had a student who was doing research for me, and he came to Sam, great guy. He came to Sam, and he flunked out. He was on a baseball scholarship and partied all the time, and he flunked out. And then he got a job at like a environmental lab. And so he was just running environmental analyses and diluting samples and doing stuff like that. And he really started to like chemistry. So he came back to school and get his chemistry degree. And then he was doing research for me. It was like 2014. And he said something about ultragrams. Okay. And I stopped and I said, what was that? And then he turned beet red. And he said they had and this is the working world, right? Sometimes you need a warm body in the lab to weigh things and write things down, right? And so they hired this person that didn't know any chemistry at all. Now, he knew a little bit of chemistry. He came back to get his degree, and he was telling me that this other person that they had in the lab was a complete idiot, and they didn't know what micro was. Okay, and so whenever it was micrograms, they called it ultragrams. Okay, and they made fun of this person, and so he was always calling it ultragrams. And I see the ultraliters, and so it just I can't not see it. And he turned beet red because they just used that as a joke, among them in their lab, the ultragrams and ultraliters, and then it stuck in his vocabulary, and he used it in front of me, and I was like, what was that? He was like beet red. And he's like, I know what a micro is. And I was like, tell me the story. So he told me the whole story. So now this is 250 ultraliters, and but you will see even like on packaging, they don't want to write the mu, and so what do they use? They use a U, and so that really fed this person's mistake because they saw UG and UL, and they would call it ultragrams and ultraliters, but it's a micro. It's a Greek character mu. But now I see it, I'll just get sidetracked. And so this is our uncertainty in that, and this is our uncertainty in the volumetric flash, the stock solution, etc. And so then we can calculate. This is the dilution calculation. And so we now know our stock solution is prepared as 100 or as 1,000 parts per billion. And then here's our three uncertainties. And we can look to see which one of those is the largest. So this, this commercial standard, the uncertainty here was 1%. And so that's going to be, 1% of 1 microliter. Let's see. No, that was the concentration. 1% of the milligrams per liter. This is the syringe that we pulled out. This is 1 part in 250. This is 1 part in 100. And this is 7 parts in 250. So 7 parts in 250 is larger than 1 part in 250. So this is so far the largest. But let's see, 7 in 250, if we divide that, it's like 3.5 per 100, and this is 1 part in 100. So this volumetric flask is limiting our uncertainty. This, is this, we can calculate, but I think this is the largest standard deviation. What?
Wouldn't it be 7 parts out?
Oh, no, yeah, that's right. No, that's right. We moved the decimal place. It's 25,000. Yeah, so this is the largest one here. Yeah, so this would be, if I move this decimal place over 2, I got to move this decimal place over 2. So this is a really good result, a really good RSD. So there's almost no error here. So that would be 7 parts in 25,000. So if it's that small a number, we don't even need to calculate it. It's not going to change our result at all. And so this is another way to kind of simplify these calculations. This one right here is again 1 part in 250. This is 1 part in 100. And so this is going to give us a 1% error. And then the end result, 11.2, that's really close to 1%, right? And so this would be our reported value for our stock solution. So, any questions on that example? If you're in a hurry, let's say you're in an exam, okay, and you've got all of these values and you see, okay, this one's 1%, this one's less than that, this one's less than that, I know my result is going to be 1%. Your largest uncertainty is the thing that governs everything. Not only that, but we're squaring those. I mean, they even get, more important. Okay, so I think that's a good place to stop. There are some other examples that are a little less relevant, but you can look at those. Precision is satisfying, and that's what we've been talking about today, but it's not related to accuracy. So you can be incredibly precise right here and still be wrong. So we need to figure out a way to check to see if we're biased or not. And we'll talk about that in I don't know, it's at least another week from now. All right, talk to you later.